Welcome to Study Loop.
Our question says that a boat whose speed in still water is 2.7 meters per second must cross a 280-meter wide river and arrive at a point 120 meters upstream from where it started, figure 53. To do so, the pilot must head the boat at a 45-degree angle upstream. What is the speed of the river current that's required to have it land 120 meters upstream? Okay, so I thought the best place to start would be to draw out a diagram. So we have here, drew the banks as the green lines and the distance between them as the dotted line y. So that is 240 meters. That's the width of the river. And then x is how far upstream we want to go, the dotted line x, and that's 120 meters. Okay. And then the velocity of the boat, which I write as v sub b, is 2.7 meters per second. Okay, that's the velocity of boat on the still water. Okay, or I'm sorry, that's the velocity of the speed of the boat, regardless of the water. Okay, and then I also write out here v of b prime, which is the velocity of the boat relative to the shore, and then v of w is the velocity of the water relative to the shore, which is what we're trying to find. Okay, and then I also write here, I denote theta as the angle between the velocity of the boat relative to the shore, v of b prime, okay, relative to the y-axis, which is perpendicular to the shore. And that is using trigonometric identities. The tangent of theta is equal to the opposite over the adjacent, which would be x over y. So theta then is equal to the inverse tangent of x over y, which is the inverse tangent of 120 meters over 280 meters, which is 22 degrees. So that's another thing that is given to us. And I write that out here. So then the question is, what is the velocity of the water? Well, the first thing I'm going to do is I'm going to equate the vertical components of the velocities to find the speed of the boat relative to the shore, or v of b prime. So that's the first thing I'm going to do. So we have, equating those two, we have v of b prime times the cosine of that angle, which is theta, I write as theta in the diagram, is equal to v of b times the sine of the angle 45 degrees, which is the angle that the boat pilot angles the boat relative to the shore when it's traveling at 2.7 meters per second. Okay, so then we want to solve for v of b prime. That's the first thing we want. We'll find that v of b prime is equal to v of b multiplied by the ratio of the sine of 45 degrees divided by the cosine of theta. Okay, so if we plug in 2.7 meters per second for v of b, and we multiply that by sine 45 degrees divided by the cosine of theta, which is 23 degrees, we'll find that this is equal to 2.07 meters per second. And that's the velocity of our boat now relative to the shore. Okay, so now that we have that, we can equate the horizontal components of the velocity to one another and solve for the velocity of the water. So let's go ahead and do that. And we have v of b prime now multiplied by the sine, because we're doing horizontal, of theta is equal to v of b. Now this one multiplied by the cosine of 45. And since we're dealing with horizontal components, the water is also acting in that direction, but it's acting in the opposite direction. So it'd be minus the velocity of the water. Okay, so if we solve for the velocity of the water, which is what we're trying to find, that's going to be equal to v of b cosine 45 minus the v of b prime sine of 45. Or I'm sorry, not sine of 45, sine of theta. Okay, so if we plug in our values for v of b, we have 2.7 times the cosine of 45 and this is meters per second, minus v of b prime, which is 2.07, times the sine of 23, right? Also meters per second. And if you carry out this operation, you find this equals 1.10 meters per second as our velocity of the water. And box this in as our solution.